Hello, this is my Lab 5 of Physics 1, and I chose the Slinky project. The main purpose of this lab is to predict and analyze the motion of a slinky when it's stretched out falling from rest. We are answering the question of whether the bottom of the slinky stays stationary, which is what it's supposed to do experimentally. For key physics laws, we have Newton's second law to calculate the velocity and position of the falling slinky. Also, for the forces that we have to take into account in our system, there would be gravitational force, drag force, air resistance, and tension force of the slinky because our system is the slinky and Earth. Gravity or the gravitational force acts in the negative y direction, to say the vector form of this force. And the drag force, which is proportional to the square of the velocity times our proportionality constant, is shown by the following formula as well. The tension force is on the bottom of the slinky and is the same, which is why the slinky does not move until the top of the slinky reaches the bottom. All of these forces added up makes the net force. For tracker, we calculated the motion of the slinky by having the origin on the bottom of the slinky set in 0, 0. We positioned this link to measure the center of mass in each frame and modeled that with the red dots on tracker. The bottom of the slinky is motionless until the full slinky falls together and goes to the ground. The tracker red data shows this with a 0 slope for a while until it starts going down. The beginning of the graph is right on the x-axis, and then when it starts moving downwards, the slinky closes, and there is a downward sloping graph. This is a single point mass with constant acceleration. We set the initial conditions in the code here. The position is 0 except in the y direction. The initial velocity is 0 throughout. I also added the gravitational constant and the proportionality constant. The proportionality constant was calculated experimentally. This is for the drag force. In the first while loop, the slinky was between the time of the start of tracking a motion and just at the end when the slinky stopped being motionless. The weight force and the tension of the slinky were the exact same, so there is no net force. Also, the momentum principle was encoded with the position and velocity update formulas. In the second while loop, the time represented when the actual body of the slinky was in motion. This is when both sides of the slinky started falling down. The weight and drag force are no longer the same. The slinky stopped being motionless and gravity is bringing the slinky down to the ground. The momentum principle here again is applied to update the velocity and position of the slinky as it falls to the ground. In the coded graph ideal situation, we see that the x-axis is stationary, just as the tracker graph had as well. Then it becomes a downward sloping graph. If we compare the results of tracker and coding, we see that the code models the tracker data very well. They both start at the downward slope around the same time, which is a few moments before 1 second mark. The 1 second mark. The tracker data trajectory is not straight, but the coded graph is. We can see that this deviation is there because tracker may not be including all the forces that could be residing at the top and bottom of the slinky, like external forces outside the system. For example, tension could be on the bottom and the top of the spring. Overall, tension and gravity cancel out in the beginning. For possible sources of error, the observed motion of the tracker data could experience those deviations because of the external forces that aren't accounted for by the model. There could also be inaccurate tracking point placement on tracker, which is another possible source of error that is human-made. Question 1 is, what does the tracker position versus time graph reveal about how the slinky begins its motion? The answer to that is that the tracker graph shows that the slinky's top stays almost motionless for the first bit of seconds, with the y position remaining nearly constant. This indicates that even though the slinky is released, the top does not immediately begin to fall. Instead, the bottom is still holding up the top through internal tension, so the top collapses downward before the entire slinky enters freefall. The sudden drop in position after this short delay reflects the moment where the internal tension disappears and gravity finally accelerates the slinky downward. Question 2 is, what if there were no air resistance in the model? The answer to that is, if the air resistance were removed from the simulation, the slinky segment would fall faster than the tracker data shows. Without drag, the only force would be gravity, leading to pure free fall and a steeper drop in the position time curve. The simulated Y values would fall below the real data, showing that air resistance is necessary for the model to match the measured motion.